What I'm going to talk about today is old stuff. But what I'm realizing from having attended this conference is that we're all such specialists in diverse areas that we don't really know even the old stuff in each other's fields. So there might be some value in me talking about old stuff. I also think that it's a duty of, it's part of scholarship is actually keeping knowledge alive as well as creating new knowledge. Otherwise, we'll end up replicating, often badly, what's been done before. Okay, so I'm an experimentalist, and as such, I'm interested in things that I can measure. In explaining phenomena that can be quantified or measured. And if we're interested in consciousness, then the question that I want to know is, what should I be measuring? How to measure it, and what pitfalls to avoid. And so there is a methodological slant or intention behind this talk, as well as a theoretical one. And so I'm going to start by just talking a little bit about psychophysics. Okay, so the goal of psychophysics is to specify the relationship between stimuli, an input, and conscious sensation, an output. And so the question is, what is the mapping? And in order to be able to do that, we need to be able to assign numbers to the magnitude of sensations, which is a process called sensory scaling, in order to establish something called a psychological magnitude function, which is basically some kind of graph that maps stimulus intensity or quality onto sensation. Okay? And this, I would have thought, is a fundamental aspect of any model of consciousness. The discipline is about 200 years old. There are various approaches to achieving this mapping. So indirect approaches try to infer what the sensory part of the scale is, but through measuring discrimination thresholds. This goes back to Weber in the beginning of the 19th century. And what he did was systematically measure discrimination thresholds. Okay? What's the smallest difference between a reference stimulus and another stimulus that can be detected, right? And then he worked out that there was a systematic relationship that explained that, which is known as Weber's law. And it's basically a simple logarithmic relationship, which you can see here, okay? And what's interesting is this applies to all modalities and submodalities. They only differ. They're very consistent across observers, and each modality has a characteristic value of k. Otherwise, the relationship is as described. Fechner, next generation, but still around 1860, extrapolated from this. He said, well, couldn't we use what we know about these discrimination thresholds and integrate across the whole range of background stimuli and use that to predict the strength of the sensation? Okay? By doing that, he came up with something that's known as the Weber-Fechner law, which is this little equation here, okay? And again, that explains quite a lot of stimulus sensation mappings. Not all of them, but quite a lot. Again, across modalities and observers. Now, the kind of things that these guys were interested in measuring were stimuli where the physical characteristics of the stimulus was easy to measure and control. But you can apply the same kind of principle to stimuli where the physical characteristics are harder to define. For instance, the quality of a picture. So, aesthetics. And in the early 20th century, Thurston came up with methodology, basically asking people to assign numbers to some judgment about stimulus or comparisons between pairs of stimuli, and used the responses using these different kinds of models to define boundaries between categories and the variance associated with the different categories. It's a precursor signal detection, in fact. The direct approach, so these are inferring something about sensations. The direct approach is simply to ask an observer to put a number on the value of a sensation. And we've heard about pain. It could be brightness, it could be all sorts of things, heaviness, loudness, etc., etc. And that's called magnitude estimation. And you can, by doing something called ratio scaling, which is basically comparing the numbers assigned to different levels of stimulus, you can then, again, come up with a simple relationship that maps the strength of the stimulus onto the intensity, the reported intensity of the awareness. This is all above threshold. This is what people are consciously experiencing. You put numbers to it. Stevens' power law, also very powerful explanatory value for things that are called prothetic measures, things like heaviness, brightness, and loudness, and so on, but they're not applicable to other kinds of measures.
Are all these K's the same, or?
No. The values of K will be specific to a particular modality and stimulus within that modality, okay? But basically, all you need to change is the K, and in this case, the A. These are simple models, but across them, they account for pretty much any kind of mapping that you can think of. It's quite remarkable. And in fact, more recently, it's been possible to unify them and show that Fechner's law and Stevens' law are actually special cases of a more general equation based on information theory. So that's the complete form of the equation. I'm not a mathematician, so I'm just going to skip this, and it's not what I advertised to talk about anyway. There's the general form of the equation, and when this term here is much greater than 1, then the whole thing becomes equivalent to Fechner's law. And when that term is much less than 1, the whole thing becomes equivalent to Stevens' law. So we have a simple equation here that accounts for almost the full gamut of mappings between stimulus and sensation. And that includes stimulus values and potentially stimulus quality. With certain assumptions, which I won't go into, but they're sort of summarized here, it might be possible to include Thurstonian scaling within this general scheme. The difficulty is only in the maths. There are so many free parameters when you're trying to do the fitting that you need to make assumptions in order to be able to do it. So the point of this is simply to give a shout to classical psychophysics. This is a result of 200 years worth of painstaking experiments, mostly by German physicists in the 19th century, but not exclusively. And we have an incredibly simple model that explains the mapping between a stimulus and a conscious sensation across everything. I'm just a little bit perplexed that nobody seems to be aware of this, because it is a mathematical model. So now the thing is, it is just a descriptive model. It just explains the mapping. It doesn't explain what's in the box. Okay, and particularly it doesn't explain how a stimulus comes into awareness. Okay, and I think that's more what people are interested in. Okay, so what's inside the box? Well, one approach to doing this is to compare different levels of awareness across a pair of conditions. Okay, The assumption is that one of the condition might, interfere with awareness, and then if you do some kind of comparison or cognitive subtraction, you might be able to identify the processes or representations that are associated with something coming into awareness or not coming into awareness. Okay? The one really critical methodological issue with this is how do you know whether somebody's aware of it or not? And as far as I know, the only way you can find out is by asking a yes/no question. The yes/no question has a particular form, which is you ask somebody, did you see it or not? Or were you aware of it or not? There's two possibilities, and they have to pick one of them. Okay, and of course, an observer can ask themselves, did I see it or not, or was I aware of it or not? So it doesn't have to, in that sense, there may be no, it could be introspective as well. Okay. Okay, so if we want to find out what's in the box, what we're really doing is we're concerned about how something crosses the threshold from from not being aware to being aware. Okay, so the concept of a threshold can be traced back to, well, probably as far as you like, but I find it convenient to mention Herbar, who was a philosopher, and he conceived of the idea that a mental event, so that doesn't necessarily have to be an external stimulus, but could be, the mental event had to be stronger than some critical amount or threshold in order to be perceived consciously. And that implies a kind of a step function. So if the stimulus is below a certain level, you're not aware of it, and if it exceeds that level, you're aware of it, okay? But in practice, when you measure, the empirical psychometric function looks different. It's shaped, it's got an S shape like this, okay? So as you increase the stimulus strength, or the signal strength, then there's a gradation between not being aware, fully unaware, and fully aware with something in between. This is statistically based on averaging trials. So it's not a step function. It's always S-shaped. And as a result, there's no obvious threshold. Okay? And the shape is presumed to be due to internal noise. So here's a model of internal noise. We assume that in the absence of any stimulus, an internal representation is noisy, and model it as Gaussian noise. If a stimulus is presented, then the internal signal increases in proportion to the strength of a stimulus. Okay, the noise is all still internal. So on those occasions when the stimulus is presented, we get a copy of the noise distribution just shifted along the intensity dimension. It's got the same variance. What we assume is that the observer sets some kind of internal threshold. Okay, and if the noisy signal exceeds that, they're going to say yes, and if it doesn't, they'll say no. And as we increase the strength of the stimulus, so by the way, just this D prime here just refers to the difference between the means of these two distributions standardized against the variance. It's just a metric of. Okay, so as the stimulus intensity increases, then the proportion of yeses traces out the cumulative Gaussian function. Okay, so that's why the psychometric function is that shape. Okay, and this pretty much accounts for everything in this way. Okay, almost all psychometric functions can be fitted approximately with a Gaussian distribution. You might have to scale the intensity axis logarithmically, so that's quite common, and that might be a reflection of the fact that neurons tend to code stimuli logarithmically. It's a neural correlate. Okay, so that's now there are two properties of this psychometric function that we should take note of. One is that the midpoint corresponding to the 50% probability of saying yes corresponds to the point here, corresponds to the point that the peak of the Gaussian distribution coincides with the internal threshold. Okay? So the midpoint of this, of the psychometric function corresponds to the observer's internal threshold. Yeah? Makes sense? So that's one measure of performance, if you like, or the mapping. The other one is that is the variance of the noise. Okay, I've just made this up, but the variance of the noise will determine the slope of the psychometric function, and that in turn relates to how easy it is to discriminate stimuli with two separate values. The steeper the function, the easier it is to discriminate the stimuli. The shallower, the bigger the noise or standard deviation, the harder it is. By definition, the just noticeable difference these days is taken as the difference in the stimulus value corresponding to probability of 0.5 and a probability of 0.75 saying yes. Okay? So the smaller the just noticeable difference, the more discriminable the stimulus is, and that's because there's less internal noise. But note that the noise, internal noise, and the threshold are separate. They're independent of each other. If the noise changes, the threshold doesn't have to change. If the threshold changes, the noise doesn't have to change. Okay? One more thing. Where is the threshold? Well, there's nothing in this model that says where the threshold is or should be. It's up to the observer to set it. Okay? So you might imagine a situation where an observer is very reluctant to say yes for some reason, we don't know why, in which case they might set their internal threshold a little bit more conservatively, in which case the measured threshold, what we measure as a threshold of awareness, is on the conservative side. We get a different estimate of the threshold. Similarly, we may have somebody who's quite lax or liberal in their responding. They like saying yes, and that would then push the psychometric function in the other direction. So the measure of threshold empirically, if we're trying to find out what it is we're trying to explain, is actually is under the observer's control. It's very difficult to know as an experimenter where the threshold actually is, partly because we're sort of inferring from something that doesn't have a step function, and partly because the observer has a response bias, which is their tendency to say yes independently of whether there's a stimulus there or not. Okay, so here's an interesting, this is one of the pitfalls about not understanding these properties of psychometric functions. So imagine an experimenter does the kind of experiment that I told you about. They're comparing two conditions, and they're comparing the measured levels of awareness across these two conditions. I want to make some inference. And they pick this stimulus value here. Okay? And they get these results. How reliable is that? Well, say another experimenter does the same experiment, but then this time picks this stimulus value. And they get, right? If you look, compare these two. Here, B is impaired relative to A, and here is the other way around. And why is that? Because they're sampling the psychometric function at different points without having full knowledge of what the psychometric function is. And in this case, you can see the two psychometric functions correspond to exactly the same internal threshold. But unless you measure the full psychometric function, you wouldn't know that. Okay, and I'll leave it as an exercise for the reader to imagine scenarios where you can have different thresholds and the same variance, or different thresholds and different standard deviations. So there are issues with this method of simply trying to interfere with awareness without some control and just picking stimulus values and not looking at the full psychometric function. And if you were doing my psychology course, I'd say, go and find out how many psychology papers have actually plotted the full psychometric function before publishing the results. Okay, so moving on to a second kind of methodology. This is the kind that relies on establishing a dissociation between performance and awareness. In some ways, you can think of this as there being a control. Okay, so we have some measure of performance and some measure of awareness. We have condition 1 and condition 2. One of the conditions is associated with exactly the same performance as the first condition, but awareness is impaired. And what this tells you is that the brain is processing the information, but the information that the brain is processing is not reaching awareness in this condition, in condition 2, even though it is in condition 1. And this is a somewhat more powerful methodology, I think. Who knows? Okay, but we still have the same question. Measuring performance and measuring awareness, we need to decide how we're going to do that. And we still seem not to be able to get away from the fact that the only way you can assess awareness is by asking a yes/no question. And there are theoretical issues associated with them, apart from the psychometric function bit. And so what I'm going to do now is say a little bit about Blindsight and use that as a way of illustrating these issues. Okay? You might learn something about Blindsight as well, but I could be wrong. So. Okay, so Blindsight is defined by Weisskranz as visual capacity in a field defect in the absence of acknowledged awareness. The field defect is caused by damage to the primary visual cortex or the optic radiations. It has to be very restricted, because if it spreads too far, then you don't get Blindsight. And then the field defect itself arises because there's a topographic map from the retina, or which samples the visual field, to the striate cortex, visual cortex. And what you would do is you know, do some perimetry. You'd ask the patient to look at the screen, flash lights at various positions along the screen, ask them whether they see something or not, and end up with a plot like this, where on this side the patient always says they see something, and on the other side they say they don't. This is a hemianope because the entire visual cortex was removed. Sometimes you get quadrantanopes, and sometimes you get smaller field defects. That's not important. And we're, I think, interested in the fact that in this bit, the absence of acknowledged awareness. So, what happens? You get a patient into the lab, get them to fixate on screen. Everything to the edge of the right of the fixation point there is in the patient's blind field. This is just an infrared camera, so that it's not visible, not as bright. It's not bright, except to cameras, and that's just monitoring fixation. You flash something up on the screen. And then what you do is you compare responses in to two kinds of questions. One kind of question is the yes/no question. Do you see something or not, or was something presented or not? And in those situations, Blindsight patient will say no almost all the time. Using the same apparatus, same setup, you change the question and you say, I'll give you two alternative forced choice question now. So I'm going to present two intervals depicted by tones, and I'm going to present a stimulus in one of the intervals or other randomly selected, okay? And just indicate in which interval the stimulus was presented, okay? Just do your best. Don't guess, just do your best. And in those situations, the same patient can score 100% correct. Okay, so there's a really striking dissociation between performance measured with the forced choice test and awareness measured with the yes-no test. And that is diagnostic of blindsight. So the question is blind? So that sounds straightforward, but in reality it isn't, because there's huge differences in interpretation and opinion about whether the blindsight is actually blind. If you look at different labs, people come up with different conclusions. If you look at different labs who've tested the same patient, they come up with different conclusions. So it's not as straightforward as you think. And I'm going to illustrate this with some published work by Zecchi and Fitch. So what they did was they asked the patient to make a motion direction discrimination, and at the same time they also measured whether the patient was aware of the stimulus or not. And they did this over multiple blocks of trials, and it was, within each trial, make the discrimination where you're aware. Make the discrimination whether you were. And there were lots and lots of blocks of trials. And then for each block of trial in the same patient, they plotted the percent correct in the two-direction discrimination. So 50% is chance, 100% is perfect. And then the proportion of trials in which the observer was aware. Okay? And interestingly enough, they got something that produced a graph like this. And if you notice, there's a whole bunch of blocks of trials here where performance was rubbish and there was no awareness. And we probably call that blindness. There's a whole bunch of trials here where there was a very good correlation between performance and reported awareness. We probably call that sight. Okay? And in some other blocks of trials, there was good performance, good discrimination, and no reported awareness, blindsight. And then in a few odd trials, there was also this curious condition where the patient couldn't discriminate the stimulus, but seemed to be very aware of it. Okay, which Zecchi and Fitch, for which they termed coined the name gnosanopsia. So this is weird. This is the same patient in the same lab with the same apparatus, but on different occasions, behaving very differently. And Zecchi and Fitch said, okay, well, probably what's going on is his brain is switching between different modes in between the different blocks. But I think that's really just a redescription of the data. Weisskranz also found this. Slightly different paradigm, again, emotion discrimination, but in Zecchi's experiment, the stimulus was always the same. There's no variation in the stimulus. All that was changing was the pattern of behavior from one block to another. In Weisskranz's experiment, he did manipulate the stimulus. So it's a moving stimulus against the background. The background is dark on the left, bright on the right. That means contrast is high at this side and low here. And what we're plotting is percentage awareness and percentage correct performance. Okay? And when the contrast is high, there's no dissociation between performance and awareness. We would call that sight. But when the contrast is low, then there's a very clear dissociation between performance and awareness. And in this case, Weisskranz decided that he needs to redefine his definition of blindsight to incorporate this. So we now have type 1 blindsight, which conforms to the original definition, and type 2 blindsight, which doesn't, looks like sight. There's a lot of interest amongst some people about whether type 2 blindsight corresponds to phenomenal vision. I think it's unlikely to be the case because there's so many changes in the visual system as a result of, removing a huge chunk of cortex and all the transneuronal retinal degeneration that happens as a result. You can get degeneration in pre-strike cortex and so on. So whatever the vision is, it's not normal. Nevertheless, that's not the point. The point is only whether there's, given what the capacity is, whether there's a dissociation between performance and awareness. Okay? And Weisskranz, instead of saying that the patient's brain is switching between different modes, suggested that the difference between type 1 and type 2 stimuli was under the control of the stimulus. So type 1, type 2 blindsight was under the control of the stimulus. It's probably more correct. So we have a situation where blindsight is both blind and not blind, and that's as close as I'm going to get to mentioning superposition. So what's going on? So let's go back to our model of Gaussian noise, okay, and look at it now in the framework of signal detection theory. Some of you know what this is, some of you don't. So apologize if I'm reverting to Psych 101 here. So for a given stimulus value, there's internal noise associated with nothing, the absence of a stimulus, and then when we present a stimulus, we superimpose the internal signal increases in proportion to the strength of the stimulus. All of the noise is internal, so you get a copy of the distribution associated with the stimulus. It's got the same variance or standard deviation, but a different mean along this axis. In any one trial, the observer gets a signal, and the discrimination task, was it presented or not, boils down to the observer having to decide from which distribution that signal originated. And the only way to do that is to set an internal threshold. Okay, so this is familiar because we've already seen this. And if the signal crosses the threshold, then they'll say yes, and if it doesn't, they say no. Okay? If the variances are, if the standard deviations of these distributions are equal, which is effectively saying if all the noise is internal, then we can use the properties of normal distributions to calculate d prime, which is the separation between the means, and to calculate the position of the threshold relative to the crossover point, using what we know about standard normal deviates and things like that, but only if the variances are equal. So when we do this, it's our duty to test whether the variances are equal. The way you do that are to plot ROC curves, and all that means is somehow or other manipulate the response criterion, plot pairs of hit rates and false alarm rates to produce a curve like this. And if the curve is bow-shaped and symmetrical, that's because you're dealing with a pair of Gaussian distributions with the same standard deviation. Okay, this is important because I'll show you why it's important. This is a graph here showing the proportion correct responses. Okay, it's a model in a task where there were 50% targets and 50% blanks, and the observers just asked on each trial was something presented or not. If they said yes all the time, they would score 50% because they would get half of the things wrong. Yeah. So there's a relation between the value of d prime, okay, and the placement of the response criterion, and how that maps onto percent correct. Okay. And so for a small value of d prime, at best you might be 60% correct as long as you're in the optimal position for. But then as you become more conservative or more liberal, That's to say, as the criterion moves away from the central point, percent correct falls to chance. Okay? Same for a more easily discriminable stimulus, that is, the D prime is more separate, and so on. And what you can see here is that even if a stimulus is highly discriminable, you can get a score from almost 100% down to chance, depending just on where the placement of the criterion is. Okay? Right. So, why is this relevant to Blindsight? Well, because what we're doing is we're comparing responses, the diagnosis, we're comparing responses in a two alternative false choice test with a yes-no test. Now, in a two alternative false choice, there is no threshold. Why is there no threshold? Because the observer gets a signal from one interval and a signal from the other interval. And all the observer needs to do is to compare the two and pick the bigger one. And by adopting that rule, effectively their decision is clamped to the C equals 0 line. Okay? So if that's the case, then what the diagnosis of Blindsight depends on comparing two sets of responses, one that comes from a two alternative false choice test, which is always going to be a reading along this axis here, and another one that could be a reading from anywhere along one of these lines. Okay? If the observer is conservative, they may have exactly the same ability to detect the stimulus in the two tasks, but in the yes-no task, they may well still be saying that they don't see the task, they don't see the stimulus, because they've got a conservative criterion. Is that all right? Is everyone happy with this? Not too Psych 101, is it? Probably. Okay, fine. Okay, well, so this could be an explanation of Blindsight. So let's test it. Let's see what happens. So just present to the patient a stimulus somewhere out there in his blind field. Very simple experiment. Do lots of blocks of trials and compare two conditions. One condition, the instruction is say yes if you see something, say no if you don't. And the other condition is a two alternative false choice, indicate the temporal interval first or second in which the stimulus was presented, and then average over lots of blocks of trials, estimate where the criterion is. And we can see that in this case, his response criterion or threshold is almost 2 standard deviations away from the neutral point in the yes-no task, and is pretty much at the neutral point in the false choice test, as you would predict. And if we want to see how that would play out for a given value of D prime or for a given stimulus value, then if we pick a stimulus value of D prime 1.5, that's where his criterion is. That's his percent correct performance in the false choice test, and that's his percent correct performance in the yes-no test, given that response bias. Okay? One more little, so why is the response criterion conservative in Blindsight? Why is it, does it seem unusually so? Well, one theory of what determines the placement of the response criterion is the Nyman-Pearson objective, which is just simply minimize the false alarms. Okay, that's a simple strategy. There are other strategies you could adopt, but it's a simple one, makes no prior assumptions, and I think it's a prerequisite for normal behavior. You would never cross a road if you falsely saw a bus coming when it wasn't there. And so when the stimulus is detectable, if you adopt that criterion, because of the separation of distributions, your criterion is going to be placed pretty close to the neutral point. But if you severely reduce the sensitivity, then and adopt that criterion, then adopt the Nyman-Pearson objective, then the criterion will be dragged away from the neutral point. You become conservative. And it is the case that if you measure the contrast sensitivity in a blindsight patient, both the spatial frequencies cut off, but also the absolute sensitivity are severely affected, and by about 2 log units. So that is really, really quite considerable. There is residual vision there, but it's very, very weak. There's another little condition here we can throw in, which is to instruct the patient to guess. Okay, let's call this the yes or guess task. Well, say yes if you see something, otherwise say no. Right? No, sorry.
Yes.
Say yes if you see something, otherwise guess yes or no. Thank you. So this is a yes or guess task. And when we did the experiment originally, part of the reason for including it was to make sure that he didn't guess in any of the other 2 tasks. You know, you're allowed to guess here. But it does throw up something interesting, which is that if you plot his position of his response criterion here, it is now much closer to the neutral point than it was before. And if we look at what this means, you know, for a given value of d prime, we can see that's his response bias in the yes/no condition, corresponding to 55% correct, not very good, not above chance, but that's his same stimulus with guessing. He's now up to about 80% correct. Why should that be? Well, remember that a response bias effectively is a reflection of an observer's inclination to say yes, regardless of whether there's a stimulus there or not. If they've got a very conservative response criterion, they're going to say no a lot of the time. But if the instruction is, say, when you're inclined to say no, guess, you're just going to you're just increasing his inclination to say yes, and that reduces the response bias. So this will work only, obviously, if the observer has a conservative response criterion, but he does because he's got very reduced sensitivity in the field. It's worth noting that a lot of people don't know the difference between forced guessing and forced choice. Forced choice is criterion free, there's no threshold, but forced guessing is essentially a variant of a yes/no task where you're manipulating the response bias, and you've got no control of where the threshold is going to be. You can't guarantee that it's going to be at the neutral point. And so that's a source of confusion.
Can I ask a quick question?
Yes.
Why does the percent correct matter for the blue line here? Because the blindsight phenomenon is about percent awareness. So the criterion should matter, but it's not about whether percentage of the awareness judgments themselves are correct. So I'm wondering whether, do you see what I mean?
Yeah, I see what you mean. Yeah. But then, yeah, I see what you mean. Maybe I'll answer it later.
Okay.
I'll carry on telling the story. That's a subtlety, I think. But yeah. In this experiment, I was really interested, not so much in awareness, but in sources, whether there's a difference in bias in these 2 things. So awareness wasn't the relevant factor. Yeah. Okay. But if he was relying on the same responses to report awareness, okay. Am I off the hook? Okay. All right. So the next question you might want to ask is: does this conservative response criterion account for all of the dissociation between performance and awareness? 5 minutes. I started at 1:15. Okay. Okay. And so one can, carried out an experiment. And this time what we did was we calculated signal detection measures. Okay. So we're now measuring D prime, which is independent of response bias. So it's a bias-free measure. And I'm just showing these ROCs here. the ROC is a control. If the variances are equal, then D prime is independent of response bias. But if the variances are not equal, then D prime varies with response bias. So you really do need to check whether the ROCs are regular or symmetrical, or in when plotted as standard deviates, they fall on a straight line with a slope of 1. They do. It's a control. And this is what you get. This patient was twice as sensitive in the two alternative false choice test as in the yes-no test when measured with a bias-free measure. And this is a very unexpected result. It's a very rare thing to find. So it shows that there's something more to the dissociation between performance and awareness. Effectively, he's on a different curve in the two alternative false choice test than he is in the yes-no test, which is very hard to explain. So what's going on? Well, psychologists have known for a long time that when you do psychophysical tasks and you repeat, you're presenting stimuli over and over again, there are curious subtle patterns in the responding, okay, which we call sequential dependency. So you get, with lags, negative correlations and positive correlations, okay? And these are taken to be evidence of small adjustments to the response criterion from trial to trial. So when we do the maths, we assume that the criterion is fixed, but in practice it moves around very little. And that's controlled, presumably in order to make sure that the criterion is centered on the flux of incoming signals. If we look at the sequential dependencies in this patient's responding in the yes-no task, we can see that there's a huge negative sequential dependency in his, if he said yes on this trial, he's much more likely to say no on the next trial than you would expect, given the overall proportions of yeses and nos in the data set. And that's exceptional. We take that as evidence that the criterion is moving around much more than it should. The criterion is wobbly. It's not being managed properly. There is an explanation of how that would work. I don't need to do it. I'll show you how it affects the maths. When we calculate D prime, we assume that the criterion is fixed, and we calculate D prime as the difference between the means of the distributions standardized to the variance of the distributions. So standard deviation, sorry. But if the criterion has variance, then mathematically that's equivalent to taking that variance and adding it to the two distributions that we're estimating. So now we've got the same difference between the means, but we're dividing it by a larger standard deviation. And so as a result, we end up with a smaller value D prime than we should. Okay, so that's, if we sort of try and work out what's going on in Blindsight, then it isn't the fact that damaging V1 is simply taken out a module responsible for awareness. Rather, it's the dissociation between performance and awareness comes around to some disruption of the threshold setting mechanism in the brain. Interesting. What do we find in normal observers? Just very quickly, there are reports in the older literature of dissociations between performance and awareness in normal observers. Here's one on spatial left-right discrimination. If you use the methodology that I've just described to you, then you find no difference whatsoever in the D primes between yes, no, and false choice responding. Okay. Same with the face detection. You find no dissociation between performance and awareness if you use signal detection methods which are not contaminated by response bias. So the situation, I think, is like this. The scheme is numerical. If you can imagine in our experiments, we might either manipulate the stimulus with backward masking, or we manipulate the observer with a lesion or TMS or attention or something like that. And then we're looking for dissociations between performance and awareness, where the awareness is being measured either subjectively, which means with a yes/no task or something equivalent, the result, and measured with percent correct measure, so that varies with response bias, or we measure the awareness objectively, as in a 2FC task, or with D prime. And if you measure awareness objectively, I don't think you will ever find a dissociation in the literature. Okay, so all of the dissociations that exist, that are, are associated with changes in response bias. That's my assertion. It'll take me 100 years to go through everything with a fine-tooth comb, but everything I have looked at, I say actually this is not a bias-free measure. So here's the main points then. So I'm not doing too badly, Kobe. Am I right? I'll probably finish in 50 minutes. So firstly, general psychophysical law is a mathematical model that adequately describes the mapping between sensory system and the quantity and quality of conscious sensations, but it doesn't explain how internal representations of stimuli come into consciousness. The psychometric function is S-shaped due to noise associated with those internal signals, and it's adequately modeled by a Gaussian distribution. The existence of internal noise means that an observer has to set an internal threshold which is susceptible to response bias, and only internal signals that exceed that threshold are consciously perceived. The blindness in Blindsight is not due to the loss of a module that confers awareness, rather it's due to abnormally conservative and unstable internal threshold. And these effects, and I'm referring to the abnormally conservative and unstable internal threshold, are not normally found in normal observers, and when criterion-free measures are used. So where does this leave us? Option A, conscious awareness is merely a correlative response bias. That's not as uninteresting as it may seem, because response bias is merely a manifestation of where the observers place their internal threshold. And internal signals that cross those thresholds are consciously perceived. So actually this is highly relevant. The placement of the criterion is the thing that we should be trying to explain. Setting and maintaining appropriate internal thresholds, therefore, must be crucial for maintaining the correspondence between performance and awareness that characterizes conscious behavior. And that's what we're trying to explain. And so understanding how this is implemented would go a long way to explaining what's in the box. Alternatively, or as well, conscious awareness relies on different sources of information to yes/no questions, which I've been talking about, and if so, what are they, and how should we go about measuring them? So that's it. Thank you.